All right, so we know how to define systems, and now we need to talk about the laws of thermodynamics. So, what is the zeroth law of thermodynamics? Well, it says that if two systems, and look how important it was that we already defined clearly what a system was. Again, it's either some control mass that we pick, or it's a control volume with either real or imaginary boundaries. And again, the control volume can be fixed over time, or it can change depending on the physical situation, because it depends how you define it. So again, really important, we already know what a system is. So if two systems are in thermodynamic equilibrium with the third system, then the first two are also in equilibrium with each other. So that should be pretty familiar to you because it's kind of just common sense. And it's also kind of like the transitive property in math from middle school, where if A equals B and B equals C, then of course A equals C. And it might seem kind of trivial, and it is kind of trivial, so it's actually not something we're going to really be able to apply to problems to get a lot of new information. But I'll just show you kind of illustratively also to help us with some more examples as far as what a system is, the following. So imagine you have some box filled with some gas, right? These little dots are representing the gas molecules, and they're pretty evenly distributed because this box has been sitting around in the room having a long, long time to come to equilibrium, meaning whatever the natural state that the molecules want to go into, they will go into that state and find that state because it's been sitting there for a long time. So if two systems are in thermodynamic equilibrium with the third system, then the first two are also in equilibrium with each other. So here's this box of gas that's been sitting there for a long time. And so the molecules have had a long time to be perfectly evenly distributed, right? It might have been that there were more over here at some point, but then due to diffusion, they all kind of balanced each other out. So let's imagine we pick a control volume now, where this is control volume A, where that's defined as everything inside this imaginary boundary. That is our system for system A. We'll draw another dashed line over here, and we'll say system B is the control volume between these two dashed lines that are imaginary. So again, system B is everything, all the gas in between these two dashed lines, and likewise system C is everything from this dashed line to the right and this imaginary fixed control volume. So that's system C. So if system A is in equilibrium with system B and B is in equilibrium with system C, well, A and C must also be in equilibrium with each other. And that was kind of obvious from the beginning because remember, this gas had time. It was just sitting for a while doing nothing, and the molecules were able to distribute themselves evenly, and we can see that makes perfect sense. So the temperature and pressure here would be the same as the temperature and pressure of the gas in here and in here. So A and C are in equilibrium with each other, just like A is in equilibrium with B, B with C. So that doesn't actually tell us a whole lot. We're not going to use that law for a whole lot because it doesn't really give you a lot of new information, but it is the zeroth law of thermodynamics. Now, what's more useful is the first law of thermodynamics. So we'll get rid of this here. And we'll talk about the first law. That says that energy is conserved. So you've already heard that probably a lot of times, and it might seem that that also may not be very useful, but we'll see that that actually can be applied to a lot of systems and tell us new information. So energy is not conserved, and by that I also mean that equivalently, energy is neither created or generated, nor is it ever consumed. It is only transferred among systems or between systems. That's the first law, and we're going to see how to apply that in a lot of different scenarios. And then the second law is that the entropy of the universe, again, the universe being the system plus its surroundings. So there's a system, there are the surroundings, which is everything that's not the system, and therefore together the system and the surroundings make up the universe. The entropy of the universe never decreases. And an equivalent way of saying that is that the entropy of the universe either stays the same or increases. And so the second law is a little bit weaker than the first, in that we know energy is never created or destroyed. Entropy, on the other hand, either stays the same or it can actually be created because, again, the entropy of the universe can go up, it can increase, so entropy can actually be created. And we'll look at how to apply that law mathematically and what that means in more detail as we go further in the course. And then lastly, there is a third law of thermodynamics, which basically has to do with the entropy of a system at absolute zero. It says that the entropy of a system at absolute zero is a constant. We're not really going to use that law in this course. This is just an undergraduate kind of level course. But just for completeness, basically that has something to do with absolute zero. What really is key for us are the first and second law. Energy is conserved, and the entropy of the universe either stays the same over time or it increases. So we're going to look at how we can apply the first and second laws to problems. We'll start with the first law, we'll go on to the second law, and then we'll see that actually combining the laws and using them at the same time, that's how we're really going to be able to analyze cycles, analyze more complicated systems, and that's going to be the beginning of this course.